Hello students, welcome back. Previously in section 1, we studied some descriptive statistics of bivariate data given by two qualitative variables, one qualitative and one quantitative variables, and two quantitative variables. Let's review the final example a little bit further because that's where we have to resume. Here's an example. We have this data set of a certain class, a score distribution, and we can form a bivariate data simply by selecting any two columns. The problem set, midterm and final exam score. Okay, so let's select these two, midterm and final, and also do the same with homework scores, homeworks 1 and 2. Okay, and here are associated scatter plots. Exam 1 and 2, homework 1 and 2. Here, each dot represents a student. So this student here scored about 90 in the midterm and about 70 in final. And we can find such students like this. Remember, these two data, exam 1 and exam 2, are two different data, yes, but they're correlated. Each data value is coming from the same elements of the population. That's why we can do all these. Okay, so much for review. Now, let's open the main topic for section 2. Do you see any pattern here? Especially any linear pattern? Well, I don't know about you, but I can't see anything here. From here, nothing, absolutely nothing. Here, maybe this one is a little bit stronger, but still it's really hard to see. After all, there are only 18 dots here. Now, what if we have more dots? Will that reveal some pattern? Here are some examples. Do you see the difference? Do you see the fundamental difference between the previous scatter plot and this? Do you see a clear linear pattern? Well, we have a line here, line of best fit, trend line or regression line. That's a proper term, by the way. But even without the line, I hope you can still see it. Let me show you without the line. Let's see. Don't pay too much attention to this mathematical code. I'm not going to ask you to do this. Okay, all right. Here's a scatter plot without the line, but you can still see a strong correlation, strong linear correlation here. The dots are packed along a certain line, which is kind of going like this. Let's bring back the line. There you go. By the way, this scatter plot is the monthly averages of daily high temperatures of Dallas and New York from 1914 to 2020. And the data sets came from NOAA website, and it's public data, but I got the data and processed and present this picture myself, so the copyright belongs to me, so I can do anything with this. The reason I'm disclosing this upfront is because the copyright issue did become some problem for some of my faculty members, some of my colleagues here, and I'd like to make sure there's no problem here for me because I created this. Copyright belongs to me. Okay, all right, let's come back to this main issue here. Now, do you see this pattern here? As you move to the right, dots are tending upward. Or look at this regression line, the line of best fit. It has positive slope. As you move to the right, the line is going up. When that happens, we say these bivariate data is positively correlated. So the high temperatures of Dallas and New York are positively correlated. And that's measured by this quantity here, R, which we call the correlation coefficient. We're going to talk a little bit more detail about this in the next section here, next subsection here. And the R value is always between -1 and +1. And precisely equal to 1, then it's an absolute correlation. So all the dots must be precisely along the line. It's 100% correlation. Here we have 0.959, so we have 96%. So that's really strong correlation we are looking at. After all, Dallas and New York are both coming from the same country, same northern hemisphere, so it's not surprising their temperature are strongly positively correlated. Here's another example, Dallas and Los Angeles. Oh, by the way, here, each dot represents a month. Each dot represents 1 month because we are looking at monthly averages of daily high temperature, not daily data. If you have daily data, then we have much bigger swing. Okay, let's go back to Dallas and Los Angeles. You still see a linear pattern and pretty strong correlation as well. Even without this blue line, you can still see clear linear pattern there and a line of best fit forming. But compare this with the previous picture. Which one is more densely packed around that regression line? Dallas and New York or Dallas and Los Angeles? Clearly the former, isn't it? Just looking at the picture, you can clearly see the difference. Not coincidentally, R value is closer to 1 for Dallas and New York. And this one still strong, but not as strong as before. We have 0.789, about 79%, still pretty strong. But this one is 0.959, 96%. This one is stronger. And as you can see, dots are more densely packed toward the trend line, the regression line. A little bit less, but still strong. Next one, Dallas and San Francisco. Similar, we have linear pattern, but more lightly packed. Still, you can see positive correlation. As you move to the right, dots tend upward, and vice versa. Also, look at this regression line, the line of best fit. It has positive slope. As you move to the right, the line goes up. Of course, they're all coming from the northern hemisphere, so it's no surprise there. Dallas and Honolulu, again, positive correlation, but compared with, say, Dallas and New York or Dallas and Los Angeles, more lightly packed. Not surprisingly, R value is smaller. All right, here's a little bit different example, Dallas and American Samoa, and we have negative correlation this time. As you move to the right, the dots are going down. And look at the line of best fit, it has negative slope. The reason, American Samoa is a US territory in South Pacific, so it's in Southern Hemisphere. So no surprise there, as a matter of fact. The season is reversed. And as for how densely those dots are packed along this line, compare this Dallas and American Samoa and Dallas and Honolulu. This one and that one. There are more dots here because this goes from 1914 to 2020 and this one goes only from 1960 to 2020. That's true, but as far as being tightly packed around the regression line, about the same. And looking at the R value, 0.66 something, negative 0.61 something, pretty close to each other, except for the sign. So no surprise there either. So in this case, you have negative correlation. The temperatures are negative correlated. As x gets higher, y tends to get lower. The line of best fit, or the regression line, is going down. It has negative slope. Now all those are governed by this quantity, which we call the correlation coefficient. Now, don't worry, I'm not going to ask you to calculate this thing. Let's just analyze this a little bit. This represents summation. So there must be some thousands of these products, add them all up. And that's what the sigma is talking about. And how many are there? There are n such dots, and divide by n minus 1. Not n, but you have to divide by n minus 1 for some strange reason. And then what is Sx and Sy? They are standard deviations. Sample standard deviations of x and the sample standard deviation of y respectively. You see, we have each individual data value xi minus x bar, subtract the mean, and that's called a deviation. Now take the square to make those deviations squared, which is positive, so that we can add them up without negating themselves. If you did not take this square, then plus and minus will cancel each other out. If you add them all up, you're going to get 0. So make everything positive. So if you have big deviations, then you're going to get big sum. And the deviation is not very much, then you're going to get little. In that case, more concentration in the middle. So those are standard deviation, Sx and Sy. Now let's come back to this formula here. Because of these, positive square root, denominator is always positive. You don't have to worry about these. Now what about the numerator? Now let's go back to, let's say, this case, Dallas and Honolulu. Okay, all right. Now, if I select xi value much bigger than the mean value of x bar is around here in the middle. So if I select something in the right hand side, then xi minus x bar is going to be positive. Also, how about the y coordinate? There are a lot more points over here than down here. So yi minus y bar, that too is generally positive. So y coordinate is always bigger than the y coordinate of the average. So if you multiply positive times positive mostly, you're going to get positive value. Now what if I select xi values from here, smaller than x bar, so that xi minus x bar is negative? Look at this diagram, there are a lot more dots down here than up there. So yi minus y bar, that too is negative. Y coordinate is smaller, so in the end you get positive again. That's what this positive correlation and this going up, this positive slope, are related. How about in this case? It's different now. If I select some big xi values here, more points are down here than up there. So when you select xi minus x bar positive, then y minus y bar tends to be generally negative. There are some positives, but overwhelmingly negative. So overall, you're going to get negative value. Vice versa, if I select something from the left, xi minus x bar is negative, but there are many more points up here than down there. So this is positive. So negative times positive is negative generally. So generally negative things are added. So our value is becoming negative. So that's how going up or down and positive and negative correlation are related to each other.